Hi, welcome back. I am doing part three of the invasive species style exponential functions problem to help you out if you need to do a do-over on the exponential functions test, or perhaps if this is next year and you are getting ready for the exponential functions test, need a little help preparing. So here we go. We have our situation with kudzu as an invasive species. It's an invasive species that is growing at an exponential rate of 53%. It starts off covering, we find it covering 25 square meters, about the size of one of our classrooms, 5 meters by 5 meters. And we want to know how long it'll cover an area as large as Mississippi, which is 125.43 billion square meters, or 125 billion 430 million square meters. All right, so the first two parts were compounding interest, but they were compounding in steps. First, just a weekly rate compounding weekly, and then a weekly rate compounding daily. But finally, the last part asks, and this is how things work more in living systems anyway, it asks about compounding continuously rather than in steps. Life doesn't tend to go in fits and starts. It tends to happen in a more continuous process. We're going to use a different equation, so it's going to be different from the structure of P times 1 plus R over N to the N times time. That time is often an X, you can say X. Okay, so we're going to use a different structure because this structure deals with compounding that's going in steps. Continuous means we're not going in steps. We're going as a continuous, never-ending, always compounding, always infinitely compounding approach. So there are no single discrete chunks of time. It's just a smear over time. So we're going to use a different equation. Instead of this equation, we're going to take advantage of the PERT equation. P times E, or Euler's number, raised to the RT power, the PERT structure. And that T can just be turned into an X. And so you can also call it the Perks equation. So we have the same initial value. So y is going to still equal 25. And then we're going to multiply that times t, which is about 2.7. And if you type it into Desmos, Desmos is fine with you typing a letter E. It knows that you're typing Euler's number or the natural base. So then we raise that to our rate. It's a growth rate, so that's positive, so 0.53. And we're not using t on Desmos, we'll use x, so 0.53 times x. And then again, we will see when that intersects with y equals our target value, which is the area of the state of Mississippi. So here we have our equation, y equals 25e to the 0.53x. Let's go over to Desmos and do it. So y equals 25e raised to the 0.53x. And now I have a new intersection. I'm going to make this one go away because they're pretty close to each other on the screen, as you can see. I'm going to make that go away. I'm going to zoom in just a little bit on where I am, a little bit there. I'm already in the right scale, so there we go. 42.144, where the last one was 42.7 something. We can see that one was, maybe I have to zoom in a bit more for us to see it. Okay, we'll zoom in a bit more. So the last one was 43.72. Now we're at 42.14. So a little more than a week shorter time. So now we go back. So we got 42.144 weeks. I'm going to round that to 42.1 weeks to get to 125,430,000,000 square meters of area. Okay, 42. It will take about 42.1 weeks for the kudzu to take over an area as big as Mississippi if the compounding is continuous. Now it's a weekly rate, continuous compounding, where X is weeks. And let me say a couple things about Euler's number. Euler's number is Euler's number, also known as the natural base, was developed as a way to figure out situations where you had continuous compounding, where you didn't have quarterly or monthly or daily. It was actually infinitely high number of compounding events that were infinitely short. So if we take a basic structure of $1 being loaned, our principal is 1, and we're going to have a rate of 100%, and we're going to divide that by n, and we're going to raise that to the n power, and we're not going to worry about time because we're just going to have one event. If we do this and we make n as big as possible, over here, this 1 over n is going to try and be 0. So inside here, the base is going to try really hard to get to be 1. 1 plus something trying to be 0 is trying to be 1. So it's trying to be 1. At a base of 1, we'll never have any growth at all. On the other hand, the power is trying to get as big as possible and then even bigger. So our base may be heading towards 1 but never quite getting to 1. And our power is heading towards ridiculously high numbers. So we take that basic structure and we put it into Desmos and we say, okay, n equals, and I'll start off with 50, and we say 1 times 1 plus 1 over n raised to the n power. And as you can see here, it becomes that. Now if I change that to 500, 5,000, each time I increase it, we get a little closer to E. I'm going to type in E here. E is 2.178 281828, and this is rounded. It goes on 4590, 4523, and then on forever. Let's add another 0, and see, we'll get closer. At a certain point, Desmos can't handle this and freaks out and decides that I think the answer is 1 because it just can't handle it. But as we increase the number of compounding events, this number here becomes closer and closer to this number until Desmos freaks out. I'm going to just keep adding zeros, keep adding zeros, keep adding zeros, keep adding zeros until Desmos freaks out. I think Desmos is starting to freak out at this point because it's starting to veer off. But here I'm at 500 billion compounding events, which for all practical purposes may as well be infinite. I get 2.71822. The first 5 digits of Euler's number are evident to me. If I had a better calculation tool than Desmos, I could get even closer to Euler's number. Euler's number is based on this structure, and what the value of this, the limit of n being pushed to as big, as ridiculously big a number as possible. We take n and take it to make it all head towards infinity, then this ends up being equal to this value, E. This is actually not the value, this is an estimate. But this is what Euler's number is. And it takes into account the whole continuous compounding, which is why we can put E here instead of 1 plus a rate and blah, blah, blah. There's more to that, but I don't have time to go into it in detail. I encourage you to investigate E. It's an amazing number. Euler's work is amazing. And I'm about to run out of time for this video, so I'm going to stop. I hope that was helpful.